Okay, fine.
So, good evening, Andrea.
Good evening, Tino. Good evening, everybody. And also, probably good morning for the ones that are in American areas. And thank you for participating in this GMI webinar. And let's allow people connecting. So maybe 1 minute more, Tino, if you agree.
Sure, not a problem. We have time.
In the meantime, we want to remind you that this free webinar will be recorded, and then you can see later and maybe share with people that cannot participate today. You can also make questions. Then Q&R, the chat is disabled, but there is a Q&R button on your bar, so you can make questions anytime. We can't stop Tino all time, of course, but time to time we will try to answer the question you are making today. Okay, fine. I think now we can start. Now it's just introduction slides, few slides for introduction. So today we are talking about de-energized to trip and versus energized to activated applications. So the speaker today, just a few information about us. There is with us Tino van de Capelle. Tino Capelle is our expert for functional safety in application, safety-related application. Has more than 30 years experience. Is our director for functional safety. Has more, I think, I realized more than probably 2,000 courses all over the years, and also in this period we are having some webinars, especially online, because we cannot travel too much. So if you have any question about our functional safety courses, you can make it anytime. Myself, Andrea Spalora, I'm a global account manager at Gemi International. I was responsible for European market, and I'm responsible for main accounts. I'm also a functional safety engineer. So about Gemi. Gemi is a company based in Italy that design, engineer, and produce a complete range of physically safe and seal certified devices for most critical application for packages like DCSs, fire&gas, HIPs, SCADA, and so on. We are working in oil and gas, chemical, petrochemical, fertilizer, mining, and food application. As we said, we are based in Italy, but with our production, complete production in Italy. And we have more than 40 experience because also the company was founded in 1993, but our former company was Econ Instruments. We have also a global presence in all 5 continents. This is some numbers. We have 10 offices beside the headquarters in Milan, Italy. Also US, in France, in Dubai, Singapore, China, Japan, and Russia, India, and so on. We are also opening new offices continuously. We have some, of course, in the countries where we don't have our subsidiary, we have our distributors. We are talking about 200 people. Oh, sorry. People. And some numbers about functional safety, cybersecurity courses that we are also arranging. Thousands of installations all over the world. As we said, we produce in Europe. We have a complete state-of-the-art technology, complete traceability for incoming and outgoing products. We test all products 100%. And also provide 5 years warranty for all our products. Some information about the certification. We have certification for European, for American markets, for Russia, for India, for China, Japan. We also have a functional safety management certification systematic capability 3. So beside the product certified, we also have certified the design. That is also very important. We're also compliant, of course, with all eyes on the ROS and REACH directive. Oh, sorry, too fast. Again. This is the product we produce. We produce safe isolators or barriers, safety relays, isolators, safety power supplies, multiplexer, termination board for main system producers, hard multiplexer, surge protection, and indicators. The last bullet is regarding our courses, which is a very important part of our activity. Some information about the customers divided by system vendors, EPC, OEM, and the users. Probably some of you are in this list. Now is your turn, Tino.
Thank you, Andrea. Thank you, Gemi, for giving us another opportunity to share some of the know-how on very specific items. Today is a very simple, generic item we're going to discuss. It's called the de-energized versus the energized to activate applications. And the basic principles, to start with this, is that for every single SIF or safety instrumented function, when you think about since the beginning of the edition 1 of the 6.15.11/2004, now we are in edition 2 since 2016/2017, the IEC 6.15.11 or the ISA 6.15.11 is now asking very clearly, you shall describe and you shall include 29 different items per safety instrumented function. That means that they're asking in your safety requirement specification to explain exactly how the safety function needs to go to the safe state. And there are many different other parameters besides this 29, but one of them, and this is the one that I highlighted here in the bottom of this slide, the requirements related to energize or de-energize to trip for each safety instrumented function. What I have done is, instead of calling it energize to trip, which I do have personally some, not say issue, I personally have some doubts about the expression to trip, because when you energize your deluge system to start and you start the pump, I got trouble to call this energize to trip because you energize to activate or start your pump. That is why in this webinar here today for Gemi, and we have done this webinar a few times in the past, we distinguish between de-energize to trip, which is the first page which you see over here, and that is the majority of all your safety loops. So when you are in the process industry, which falls under the application standard called the IEC 6.15.11, and for the process industry, what do we call process industry? That is the oil and gas, that's the chemical, the petrochemical, and new since 2016-2017 edition 2, they added 2 new applications, being the pharmaceutical industry and the food and beverage. So in general, for the process industry, I would reckon that probably between 95 to 98% of all the safety loops out there in the field are all based on de-energized to trip. And de-energized to trip is also called often the idle current principle. That means you remove the power, you remove the energy, and your safety function is supposed to go to a safe state. We call this fail-safe principle. So when you are programming your safety PLC, you will see that in normal conditions, when everything is okay, your digital output may be energized to keep your production running. The moment you want to stop, you're going to de-energize, you're going to remove the power in the hope that your solenoid will move to the right position. It will vent the air. It will vent the air of the actuator, and your final element will potentially go to the state it was predefined. If it was a fail to close valve, it will go to the close position. If it was a fail to open valve, it will go to the open position. Common examples of subsystems that transition a system into a safe state are typically called the shutdowns, or we call them very briefly, we call them the ESD, emergency shutdown system, or the trip systems. So summary, the de-energized to trip is the most known, let's say, way of making or building your safety systems. And you may think it sounds simple. It is actually not as simple as you may have thought before. That is why we thought with GMI, let us make a webinar to make a clear difference between energized to activate and de-energized to trip, because sometimes we're going to mix signals and we may inverse signals with some interposing relays, which is also part here of this webinar today. I start with a very simple example of one single safety instrumented function. An instrumented function for us starts from left to right. So from subsystem 1 all the way till subsystem 6, that is one safety function. So assume that you have a 1-on-1, as we call this architecture, a 1-on-1 safety loop. We are trying to measure a process value in the field. We may have to go over an isolator, and I took here one of the GMI isolators in this picture. So we have to isolate the signal coming from in a zone classification inside into my marshalling cabinet to be wired inside a safety PLC. The safety PLC itself will actually contain the logic or the interlock or the application logic, as we call them, that will be here inside the safety PLC. And if your process value in the field has reached a trip point or triggered the alarm that you have programmed before, you may want to do something. So you may want to potentially open or close the valve. So what is this interlock doing? It will send the signal to the interposing relay, potentially again an interposing relay, and this relay will take over the load of that solenoid, which is here subsystem number 5. And a subsystem number 5, that will then eventually take the instrument air away for your actuator of your final element. So from left to right, from subsystem 1 all the way till subsystem 6, they all start to work. The moment it leaves the safety PLC, it starts to work in the de-energized to trip. That means we want to remove the power. When you cut the cable, when you lose your power supply, when you lose your instrument there, the final element should be configured as such. If it would be, as an example, a spring return actuator, that means if you remove the instrument there, providing it can vent the instrument there from the actuator away, that the spring and the torque of the spring will be able to close that failed to close valve. That is a normal working principle of any safety loop that you may be dealing with. Okay, Andrea, we are having in the very early beginning of our webinar here a poll question. Let me introduce the poll question maybe to the people. The poll question is to get some interaction coming from you. And we have here the poll question asking the following question to you. What would be the role of the power supply, that means the field power supply, for your instrument or for your subsystem/devices in a de-energized to trip application? And I may want to warn you, it's a little bit of a tricky question because we ask you here for the role of a power supply or a power converter, enabled to feed the power to the field, to your instruments, to your subsystems. A potential A question, A answer is a reliability issue for that safety instrumented function, that is A. B, it is all to do with an availability issue for that safety instrumented function. C, it can be both a reliability and an availability issue for that SIF. D, it is irrelevant for a de-energized to trip application. E, none of the above. So we leave the poll on a little bit longer. So there are no points to gain or to win. There is no personal name behind who is clicking here the answers. It is just
don't be afraid. So Tino,
okay, I think
we'll leave again another few seconds and then we'll stop because there's still people are voting.
Yeah, but I think we are having a very good vote today. So we have active people. We are early in this webinar also, which is good.
Yeah.
Sure. You could share that if you want.
Okay, I can stop in a few seconds.
Okay.
Then, okay, and poll, and we can share the results.
So we have 25% is believing that this is a reliability issue for that safety instrumented function. And I have to say, for sure, it is a reliability issue. So that is certainly a correct answer already. Then the second one, B, it is an availability issue. There we only had 15% of the people who voted. And I would say certainly for the availability issue on the SIF, we will explain that in a minute, but there are also in a de-energized to trip, even in such an application, there is also an availability issue to do with the, let's say, the role of your power supply or your power converter. Of course, the people, 50%, so the majority took, it can be both reliability and availability. That is the most complete and the most correct answer. That means certainly I would agree with answer C. That is the most correct one. And D, it is irrelevant for a de-energized. That is often, let's say, thought of by some engineers that a power supply can be any to feed your instruments, that it has no issue towards reliability or availability of a safety function. I would not really want to agree with that. So I got a slide prepared that I will explain a bit more why we have just stated that. I will stop sharing this, Andrea, and I will continue. Okay, so fundamental sys hardware concepts is one of the, let's say, the foundation for engineers in design to understand how to design their safety systems. And the normal process conditions, that mean if everything is working normal, every subsystem has to be failure-free. That means from sensor all the way to final element, it has to be working as per requirements. The question, of course, will be, and that is not for this webinar, we have covered this in another webinar, is how do you know that your subsystem is not working if you do not test it? In other words, if your final elements, which are stuck in a position for a very long time, are stuck there for, let's say, months or maybe years, how can you know or how can you estimate that this will work if you cannot test it? That means we will have to do something called proof test. Proof test, interval proof test coverage are two items which we have discussed in other webinars. But when I focus here on this one, let me take here the role of the power supply or the power feed to all those subsystems. And the power supply itself, of course, needs to be reliable. That means that power supply needs to be accurate. There will be an accuracy of maybe plus minus 1 or 2% on it. We need also to monitor in that power supply if we have a safety rated power supply. We also will rate some, we also will diagnose or check things like under voltage, over voltage, and those two informations will be actually fed back in my diagnostics. And that is why, like in GMI, they have come up years ago with a SIL suitable power supply. And in the beginning, when you are talking to engineers and you're saying, have you used a SIL rated power supply? They said, we don't need that because we have to de-energize, we're removing the power to trip anyhow. And I said, that is partially true. That's certainly not untrue. However, if you think about your power supply itself, where you feed your subsystems with, what is happening if you would have an overvoltage? Assume you have an overvoltage and it's damaging, for instance, the coil of a solenoid, but you're not aware of it. Like really happened in reality, it's with some of the large end users, and you're having an overvoltage that was not marked by any fuse or any protection, actually was damaging some of their final critical elements, leading into when they wanted to shut down some of the safety loops, they did not work since they were out of service. And since the proof test interval was typically months or years, they haven't found out until it was too late. And that is one story why under voltage, over voltage, both of them needs to be carefully monitored. Also, your power supplies needs to be protected against the latch up and the high-end rush current. That means that those are two different topics again, which are all described in a reference. And I here took the reference in that middle bullet here. I call this the IEC 61508 part 2. For those of you who do not know what the IEC 61508 really means, well, it's a functional safety standard for any component where you have an electrical signal or you have a electronic sub-component in it, or you have a programmable electronic safety related system. In short, we call this the functional safety standard for EEPES subsystems. That means that any manufacturer claiming that their subsystem is SIL X suitable, will then enable to prove that and to have it assessed or accredited. That manufacturer will then prove that they have followed the 61508. And in that 61508, there are very clear measurements in the hardware section of the standard, which is part 2, where they will talk about the effectiveness and the techniques and principles for avoiding the failures and for controlling the failures. So reliability from a power supply for a subsystem could actually damage the subsystem. That is one. Other side is the following explanation. When you say de-energized to trip, it's also true that you cannot turn off the power from your entire site, and you can tell that your entire site is at that moment already in a fail-safe state. You may have to shut down in certain sequence. You may have to have certain times still availability of a certain, let's say, power to particular subsystems or safety loops. So availability, we have been doing availability since the 80s. 70s, 80s, when I was a young system engineer or a instrument engineer on site, we were using normal power supplies because SIL did not exist in the 80s. It only started to exist in 1997 by the introduction of the 61508. So before that, we were using normal power supplies. And of course, we were seeking also power supplies where we could do things like load sharing. We could do like a network with diodes, that we could do the load sharing in the back of the plane, in the back plane of the power supply, for instance, in a 19-inch rack. So we could feed and we could start to build up some availability, meaning that if one power supply unit would have been failing, we still would have the other one to cover and to back us up if we would have a failure in one of the other ones. So about redundancy and availability, that is typically done with load sharing and some information that they will share in between those, let's say, active power supply units. If you want to know more about specific power supplies, well, then there is another GMI webinar, why standard power supplies can be used in a SIF. And I'm even thinking that this is here also led by Andrea and his colleague, who is also providing that webinar. And as Andrea was saying in the beginning, for those who join us later, every webinar of GMI is recorded and is actually, you can find this back on a YouTube channel from GMI, where you can see all previous. And in the meantime, it's quite impressive. I've seen like 40 or 50 different webinars because I have checked myself to see which webinar we have done lately. So if you want to go more in depth on power supplies, I would advise you to have a look at the previous webinars. The last bullet in normal process conditions is that your instrument air, of course, needs to be available, needs to also be, dry air, needs to be controlled, needs to be accurate, needs to be available when you need it. So there's also something which is a crucial point in a normal condition. Now we're gonna go one step further. So we assume that everything was working normal. The power is accurate, the power is available, my instrument air is there, everything is normal. And now our sensor that is somewhere in our installation, let's say it's a pressure sensor and is actually starting to measure that the hazard is about to happen going into the high range of our trip point. Once actually my sensor, my analog input module is actually measuring the value that it goes to the trip point in your interlock, well then from that moment onwards, your logic solver, means your safety PLC, will actually send a signal to the digital output module, and that digital output module will try to de-energize the power to the field. Like with many system manufacturers of safety PLC, sometimes their power supply, their digital output rating for current and power is maybe not suitable to power the solenoid, or they may have some other reasons why they want to have an interposing relay between their system and the field. So once you go through an interposing relay, that means that relay is actually acting as the final command to give a demand to your solenoid to de-energize the coil, enable for the coil of the solenoid to actually relieve the spring in that system called the solenoid, to remove the pressure and actually to vent the instrument there, so that the actuator of your final element can start to go to the fail-safe position. And I took here in our example, said the solenoid will de-energize the coil, as I just explained you, and vent the instrument there. But I took here in our example a shutdown valve, which is a fail-to-close valve. So assume that you have a pipeline, assume that the high pressure was, for instance, measured with your analog input, was recognized in your interlock, was sent a signal to your digital output, actually was resulting into my interposing relay opening a contact, taking away the load for the solenoid. That means that from that time onwards, it's down to the final element to go from maybe full open to full closed position, and able to isolate the flow in that pipeline. I will not talk here about the torque in the valve and what is needed for closing the valve, or the valve signature, or the full valve stroke. Those are all details which in this webinar we will not touch. We will purely speak here about the principle of a de-energize to trip. So what I did was, I was asking to Andrea previously to give me some examples of some of the product lines from GMI. And he has given me here 2 numbers of GMI typical relays. And in that relay, you can see here, I call this typically the internal kitchen. Internal kitchen means it's more than one single contact. That means that the configuration inside that relay is from a sudden intelligence that they will have more than one way to take away the power. For a very simple reason, if they would have selected one single contact, and this one single contact would not be able to open, well, then the interposing relay would fail to de-energize. And of course, in a safety related system, we don't want to have that one internal failure, like in a SIL 3 classification, which those relays are, would actually be approved for de-energizing. So summary, enable for the manufacturer to achieve this highest level, which is the SIL 3, with the systematic capability of 3 on such type of devices, there will be more than one way to shut down the power to the field. So modern safety PLCs, typically, when you go back to the digital output of the safety PLC itself, they will work with some intelligence inside the safety PLC platform that can only measure to the last terminal, which is a terminal from the digital output module. They cannot go further to the solenoid, because in between here we have the interposing relay. That means that once the intelligence, together with the watchdog timer in the safety PLC, knowing that they want to send out a 0 to the field, and the watchdog feedback signal would still measure a 1, they know something went wrong, and they will try to shut down, isolate first the channel. If that will not work, some vendors will isolate the complete module, and other vendors will simply shut down the complete I/O chassis or even the complete PLC if they don't trust what type of I was just reading a question and I was distracted, sorry for that. So the diagnostics actually will read the feedback signal. If they don't trust it, they will simply shut down the power to the field. So providing that you have the interposing relay here in the middle, that means that there will be multiple ways, also with some measurement feedbacks here, enabled to remove the power to that field. Again, there's a second webinar that I can recommend, because I'm not here the GMI product specialist, and I'm not here also the relay specialist from GMI, but there is a dedicated webinar that is explaining you more details about this. The one we show here has 2 normally open contacts here in both, let's say, wires, or in both connections to the load here of the solenoid of this final element. And if I go one step further and I go more towards the intelligence, which actually would stop from your, let's say, digital output module that does not reach the field if it is interrupted here with an interposing relay. Well, the interposing relay, now that GMI has been on the market for many years, that is actually how I came in touch with GMI years ago when I was still doing some consultancy for other business. They provided a interposing relay with quite some sophisticated intelligence inside. Means they have a kind of a diagnostic based system, which is of course a CPU diagnostic based intelligent processor sitting inside that small module called the interposing relay. What they actually will do is they can monitor from the interface relay being itself, they can monitor the over voltage, the under voltage, they can monitor the currents to the field. So they can actually monitor completely the load to solenoid valves as an example. They mention here beacons, strobes, sounders, etc. And that's power that actually is sent to the field coming from the power supply, which is fed coming from one of those reliable power supplies. Well, that diagnostics can be fed back either to a contact signal or either through a Modbus communication inside a communication platform. I think you heard Andrea saying in the beginning that GMI has a whole range of products to communicate or interface with all the leading, let's say, BPCS vendors and even with some ESD vendors on the market. Well, that is what they are working together, enable to, as an example here in this case, feedback the diagnostics results back into your control platforms. I have here an example. I have here an example that when everything is working well and the safety PLC is actually asking to de-energize the output to the field, well, the de-energized of a digital output will take away the power from the input side of the safety relay. And the safety relay itself, or the interposing relay, will actually be then being commanded to open those contacts so that the load to your final element would be removed. Once it is removed, even then, such type of diagnostic-based relays can also monitor still like earth leakage, or even also some end-of-line resistor, or can get also feedback from the load of the current, of the load of your resisting of your coil of your solenoid. So that is here in a energized functionality where you still have power coming from your digital output. Once the output is removing the power, then that will be removing the power to the field. So they call this here load on, and that second one is here the load off. So we handle the digital output module, which is from the safety PLC with some intelligence inside. We handle now the safety relay, which also has some intelligence inside the safety relays. Now let's talk about one of the smaller subsystems, which is the solenoid. It's typically the smallest one in the entire loop. I haven't said it is the cheapest one. I've just said it's one of the smallest subsystems in your safety loop to de-energize, to take away the instrument there to your final element. And I took here a system, which is one of an ex-colleague of mine, still a friend of mine, which is showing here a Silstroke 3 box. That's a company out of Houston, out of the USA. And that is here the enclosure you see here on the left-hand side, which is like a stainless steel box. It has some stainless steel box with in the front, they have some push buttons where you can actually test some solenoids if you want to test them manually. And the story is when you open the box, you can recognize here two manifolds, and those two manifolds are configured in a certain way that at the end of the day, your air in to air out to your final element is actually a 2 out of 4 with a D4 diagnostics, where the diagnostics was built here with a particular PLC. So what it is doing, it is block and bleed. It is stroking those solenoids at all time. There is a pressure transmitter here on both sides feeding back the pressure on those manifolds to prove that those solenoids are still actually moving. And you can see how complex that certain instrumentation will start to go. And the simple reason is this, as followed. Can you go to fail safe in case of an internal failure? And if you have taken one single solenoid, you take a three-way solenoid, one single solenoid, and you de-energize the coil of the solenoid, and the solenoid is stuck open, you will not be able to shut down. So what they have done here, they have taken multiple solenoids in a certain configuration, which is done by this, those two manifolds. In the middle here, you have a mechanical latch switch enabled to test one of the sides of those manifolds. You can test the left side or the right side, keeping your plant and available and protected. If you would have one solenoid and you have to test this one solenoid, well, I can tell you, if you remove the power of that one solenoid and you only have one single solenoid to your final element will start to close or start to open. And maybe your production people will not be happy or will not allow you to do that. And that is why those type of boxes are often used when both availability and safety is actually an issue for certain clients. So the solenoid is a very simple subsystem, and excuse me calling this a simple subsystem because it's just moving the instrument there, let it through or not. And the question is, as I said before, what are you doing when that one single solenoid will be stuck open? Because the majority of all the failures in the field are not in the first 4 subsystems which you see on the picture. Unfortunately for those vendors, it's always at the end that we have the problem. Saying more, if you look in the field, if you look in the reality with the end users, I always am astonished to learn that the end users have often no idea what is the useful life of some of their subsystems in the final elements. Furthermore, when you talk to an end user, they typically will tell us as safety engineers, they will say, we want to test no more than once every 3 years. Do your mathematics, do your tricks, doesn't matter what you do, tell us that we are allowed to run the plant for 3 years. They then come up with a certain cell class on this one single solenoid, one single final elements. They cannot test it for 3 years. And then the moment that you try to move it, because you have no partial stroke, you have nothing on those shutdown valves, the moment you try to move it, you start to learn that the valve is not moving. That means your safety availability is totally jeopardized because you did not maintain maybe as per requirements, that is one. You did not take care of your mission time. Is a lot longer, often in many cases, the mission time on your final elements are a lot longer than your useful life. That means that sometimes the end users, they will only replace one of those elements when they are broken. As long as they still do something, they will not replace anything. And that is, of course, not a very good safety culture. Coming back on our de-energized, we assume that the moment we will de-energize our solenoid, removing the instrument there, that the actuator or the spring return actuator in this particular example will move the valve to the right position. Coming to the last final element, which is, of course, one of the most, let's say, critical parts in our industry, our safety instrumented function, which is controlled by a final element, fail open or fail close. Well, the problem we have, and we have to face the problem here, the problem that we have today, and we are 2021, is that until today, there is no dedicated functional safety standard for subsystem assemblies like final elements, like shutdown valves. The good news is that soon, I cannot tell you when, because of the whole corona, everything starts to slow down. But there is a new standard in draft, which is the one here on the bottom. It's a Synelec draft. It's coming from a technical committee called 69, and it's a certain work group number 1 with a reference here 1456. That's a Synelec work grouping committee who is working behind the scenes for the moment on a functional safety standard exactly to combine subsystems together. So what is happening today, because we had no other standard, since there is no other standard, our accreditation specialists are all using the framework or the backbone of the IEC 61508. So if I would take a, let's say, final element with no EEPS inside, they still take that standard routes to try to predict through a mechanical reliability, FMEA, failure mode and effect analysis. They will try to predict the reliability of such type of devices. What is happening in reality is that some end users or some, let's say, engineers, they will buy 3 different subsystems. Let's give you an example. They buy a ball valve from vendor A. Vendor A has no notification at all from any SIL suitable qualification on this metal piece called the ball valve. They buy an actuator from a vendor B, and that vendor is giving them a piece of paper saying SIL X. And then they may buy a smart positioner with a other piece of paper, say SIL X. And all of a sudden, internally for the calculation on the prediction of the availability of the safety loop, they will start to call this assembly of subsystems, final element. They will call it SIL X as per the paper given by the actuator or by the smart positioner. But it should be the complete combination of the entire subsystem that makes that ball valve to go to a shutdown position if needed. That means that we need to look further than only the piece of paper of a actuator, which is a standalone unit or a standalone subsystem or a smart positioner. In other words, it does not make your valve safer by buying a SIL X actuator when the ball valve is mechanically stuck. Those are items that needs to be aware of. And I'm sure that if you are a practical engineer, that you know exactly what I'm trying to aim for. That means that in the future, there is an urgent need that those sub-assemblies, being the final elements, will be under the microscope and will be, as per functionality, be judged what type of safety integrity level can I achieve with maybe that one single valve or maybe with that redundant valve configuration. I got a second poll question for Andrea. In the meantime, I will read some of the questions. Okay, I will read this in a minute.
Yeah, sorry.
The other poll. Okay.
Yeah.
So the question is as follows now. It's to do with the IEC 61511. Which hardware concept, if you look on those subsystems, can be SIL suitable / compatible? And I give you here the first hardware concept. De-energized to trip is in your prevention protection layers. That is a hardware concept which is acceptable by the 61511. B, energized to activate, which is classically in the mitigation layers, in the mitigation protection layers, can be accepted or suitable, compatible with the 61511. C is both A and B. And D is none of the above. I'll let you think about this. In the meantime, let me read that question here.
Yeah, please, there is a question interesting. Maybe you can pose to the other people also.
I got here a question from a person asking me the following. For a control room that we need to trip a motor, the question is if the MCC has to be part of the SIF. That's a very valid and a very good question. I would call it a very good question, that it is true that our digital output from our safety PLC systems can actually or de-energize one of those solenoids, one of those valves, but can also equally de-energize or give a command to the MCC to start or stop the motor. Because what is safety for us? Safety is nothing more than open or close a valve, start or stop a motor. The motor can be turbine, the motor can be pump, so it can be any motor driving a unit. But of course, the MCC needs to be an integral part of your safety reliability estimation on the availability for that loop. I will rephrase that. If your MCC is using a single contactor or a single relay to power the motor, and the single relay does not want to open the contacts because of welded contacts, well, then the MCC will stop your entire safety behavior of your loop. That is why we do have on the market SIL suitable MCC units where there is some redundancy, diversity, intelligency built in inside that one single MCC, just to avoid the problem which I just explained you. If you would use a single relay MCC based unit, and that single relay has a mechanical internal failure, potentially the relay will not be able to remove the power or to power on, depending on what type of application you use your MCC. So yes, the MCC is certainly also part of your SIL story on your safety loop. Right, in the meantime, the poll, I think we can stop the poll, Andrea, and we can share it.
Yeah.
Right, well, again, it's repeating nearly the same structure as our previous poll, which was not the purpose, but A, de-energized to trip is of course a correct answer, is also suitable to be used for the 61511, as well as the second answer B, energized to activate, which you can see it's a very small group who is believing that it is only the energized to activate, but I'm happy to see here that the majority Maybe you have seen the webinar before or have looked at the webinar before, but both A and B, that means both energized to activate and de-energized to trip, which are the majority of the loops, but both concepts or hardware concepts are approved and are actually referred to as to be suitable by the 6.15.11. And I want to say the following statement to that. The energized to activate is actually being added in the new edition 2 of the 6.15.11, because basically, frankly speaking, edition 1 was only looking at the prevention layers, which are classically de-energized to trip. The new technical report number 4 by memory, released in February 2020. I think it's even somewhere in my slides, but I can't remember now. That technical report 4 from the 6.15.11 released in 2020 February is now stating that it was a misconcept to believe that the mitigation, meaning energized to activate loops, do not have to be built reliable. Therefore, they even state that for all fire and gas application, a minimum SIL 1 would be required for a good engineering practice according to the IEC 6.15.11 technical report number 4. Okay, I will stop sharing and I will continue to look at my time. The opposite topic for this webinar is also the last topic, is called energized to activate. And you can say, well, that's just the inverse logic, which could be correct. But if you think about it, what was the whole topic with de-energize? In case of an internal failure, can I go to shutdown? Opposite story now. In case of an internal failure, can you activate the power to the field? And that's quite a challenge. If you think about it, if you take one single subsystem and this one single subsystem configuration has an internal failure, how will this one single subsystem actually go to activation when you need it? Because the internal failure may stop that. That means you may have to think a little bit further than just say, oh, it's just instead of a 0 logic, it's a 1 logic. We just program it different in our safety PLC and the rest will be taken care of by the instrumentation engineer, which is partly true. But there are a few items which I want to highlight. Energized to activate. Some people, as I said before, call this still energized to trip. Even in the standard, it's called energized to trip, but I like to call it energized to activate. ETA or energized to activate is never fail safe. Means if it will fail, it will never go automatically to a safe state like we have to do with a de-energized to trip. Simply reason is because for that energized to activate, we need the energy, we need the power. We need that to be carried over, enabled to have the safety function being carried out. Power in this type of safety loops means your power supply, the availability, which we mentioned before. Now the availability becomes the issue of safety, not only the reliability, but also the availability is one of the key issues or fundamentals for your energized to activate to be executed. Common examples of an ETA or energized to activate applications are, of course, the fire and gas, like the loose systems, fire suppression systems, foam systems. High voltage protection systems are classically also built, energized to activate, alarming systems, etc. Since in a normal operations, the loop has no power, that is where you will find the line monitoring. That means the digital output modules from the safety PLC that are selling you the line monitoring module. Actually, the digital output module has also a, let's say, an analog input circuitry in there, because they can measure the current that goes all the way to the final element or to the end of line resistor. Of course, when that final element or end of line resistor is interrupted, because you need to convert some power or you need to accommodate some higher power outputs, etc., then you go through an interposing relay. Well, then that line monitoring capability from your digital output module is stopped, as I explained before. That means this good information from the diagnostics, like the line efficiency, open short circuit, loop resistance, leaking, earthing, etc., is all gone if you have an interruption by the interposing relay. That is why that functionality that was before in your digital output module can now also be built in your safety relay. And that information of that diagnostics information can be fed back, as I explained before, inside your control platform, being either your BPCS or your safety PLC. Now, often what we see in the industry is that people will start to mix that. They will actually mix the de-energized to trip modules, digital output modules, with the energized to activate modules, even in the same chassis. That means that the system manufacturer itself or the safety PLC will send a signal on the backplane to those modules. Those modules will actually do two different actions, and then those actions needs to go in the field either to take away the power or to energize. Now, if you think about that question, the last bullet here, it's true that in reality, it's very rare, it's very unlikely that if you are on site, that you will see an energized to activate system to spuriously, means with no reason, starting to activate, starting to sound the alarm beacons or starting to open the deluge valves, etc. That's very rare you would see that. Opposite, if you have a de-energized to trip application, it's very likely that you have witnessed where a loop is losing the power or a loop is tripping for no reason. And that is because of the fail-safe principle. So somehow it must be a sign to you that it is clear that we don't have a unwanted power up the output when we don't need it, like we have a de-energized to trip where we don't need it. So somehow the design must be different. And that's what we will explain here. The safety PLC with align monitoring is have often not the necessary interface to accommodate the power that is needed for your final loop. So you go over a line monitoring module from a interposing relay. And that type of data is then being fed back in your safety PLC. And if you want, the safety PLC can still take credit for diagnostic information that is coming back from the system to know what the availability of that loop really would be. And I have given here, I've been giving two examples from Andrea or some of the colleagues from Andrea. And the first one that I will explain here is that sometimes it is not so straightforward if you open the cabinet. I give an example. I have seen an application where the de-energized to trip digital output, the normal modules, were used for energized to activate loops. And they were using here a interface of relay, which was then the second one. That's the second slide. Let me first show the second slide. So the de-energized to trip digital output was removing the power. And the interface here from GMI was actually doing just the opposite, was energizing the output to the field with this kind of architecture in here. Again, it's more than one single contact. Again, it will be with diagnostics, intelligence, feedback signals, and all that. Summary. You're energized to activate with a normally closed contact means when you de-energize the input of the relay, the contacts will go close and will power the load to the field, enable to energize to activate your final element. Coming back on the other one, the first one, what I want to show you, that is here with a normally open contact. That means that here energize the relay input, you will energize the load. So here you power up the load. So you power up here the input of this module, enable here to open the contact on the loads. So you have a direct load and you have an inverse with both different contacts, normally open and normally closed contacts in those type of relay. Please, could you show me the sheet 28, which is this one over here? Okay. That's sheet 28. Someone is asking me to show sheet 28, so I do not know what the trigger was to show the sheet 28. I hope that you can see that Andrea is answering live. So you will have also the sheet. So every let's say, presentation which we show you is not only recorded and shown later on the YouTube channel, it is also being saved in a PDF. I almost said a PFD, in a PDF, and that Acrobat version will then be sent to your email address as you have registered. I have to a little bit hurry up in my timing because I still want to have some questions and answer time also open. And we collected, during the registration, we collected a few questions which I did some effort to try to answer them up front, so I will then share them with you. Conclusion. De-energized to trip is a very simple principle, remove the power. It's a fail-safe solution. Yes, it's true. The question is, what will you do in case of an internal failure in your subsystems to de-energize and to actually close or open the final element? That is my question that is actually sent back to you to think about it, enable to create the right architecture for your subsystems. And the de-energized trip is certainly easier for instrument engineers and engineers who design it, also to maintain it and also to understand it. It's classically the ones we typically use in prevention layer, which I told you before. 95% of all the safety loops are de-energized. Energized to activate is often a little bit more, call it engineering mess, because people start to do all kind of inverse, reverse throughout the, let's say, configuration, towards the hardware configuration or the wiring or interposing relays, etc., etc. So that needs a little bit more closer attention for people to understand how it should really work, to energize the final element to go to the safe state. And it's frequently taught that the de-energized trip does not need a reliable power supply. That's my last message, I think, which I clearly indicated in the beginning of the webinar. And as we said, the last bullet here, since February 2020, that's where I remember the date, the technical report 4 of the IEC 61511 is now also including that mitigations must be built reliable. Before I will close and give back the word to Andrea and able to run the questions and answer, a very quick summary on the support of GMI. We do IEC 61511 lifecycle support mainly to provide you those type of activity support, going from PHRA to LOPA to SIL verification, determination. We also help on functional safety assessments and also functional safety management. And the last one here, we sometimes help some engineering companies to define the safety requirement specifications in compliance with the 61511. The new baby on our group of support, it's not a new baby anymore because they are there now since a couple of years. But we have some additional, let's say, team of experts who are helping us with the IEC 62443, which is clearly the OT security, which is a requirement from the 61511. You shall carry out security risk assessment. So we do industrial security management and assessment. And of course, we also give some supplier, let's say, assistance for security achievement. Last but not least, one of my key functions in the organization of GMI is to provide the functional safety education and training, especially for SIS competency review program. We are in the middle of finishing off this week the one for Europe. So tomorrow is the exam day. But if you would have wanted to join, well, you just missed it. We just finished. Tomorrow is the last day. We have some more coming up. So on the website of GMI, or even on the TLV Rhineland website, you will find some of the training we are providing. We also provide cybersecurity training, the fundamentals, and the security risk assessment. We do customized in-house trainings, mainly virtually. As Andrea was saying, we still travel as much as we used to do. And of course, there are still some more free webinars to follow. Last but not least, this is the best book in the industry, where we have more than 50,000 copies worldwide already distributed. It's a hardcover book or it's an ebook, whatever would be your preference. You could register and you could obtain one of those books coming from GMI. With this, I will close and I will stop share this, Andrea, and I will go back into, in the meantime, I will read the question.
Yes, please, Tino, there is one that I wanted that you answer.
Okay, I have to share here now the other. Okay, I'm looking for the other Q&A, which I finally found. So let me first click share the Q&A and then I will read the question loud. That's revision 3. Okay, share this one. And then I say start. And in the meantime, I don't think SIL 3 certified MCCs are available in the market. Please clarify. You could be right. On the other hand, as you can appreciate, I have to be neutral. So this is not the purpose to make marketing for other vendors. If you do your homework, if you talk to some MCC vendors, I'm pretty sure you will find a solution, even though if you have to go for an MCC into a SIL3 application. In the meantime, I get another question. Do we have SIL3 certified analyzer for process industries? That's another good question, very similar to the other one. So if you send me all your product questions for vendors, which I cannot answer or I'm not allowed to answer, then I have to apologize, I have to stay polite. I will say again, yes, I know of some analyzers who have done some reliability study on the behavior of the analyzer itself and do have some SIL suitable, compatible instruments or devices on the market. All right, Q&A, questions and answers. So we selected some questions and answers. And if you agree, Andrea, either I can read or you can read, but I can read the question and I can read the answer also. It's up to you. What do you prefer?
I will read it, so I will do something. Otherwise, people say that I'm just here for nothing. Okay, but don't worry. I laid a ladder webinars. If you want to go to our website, so you see, as Tino said, the power supply webinars dedicated for power supply for relay with the line monitoring and so on. Please go to our website and you will see other webinars. In the meantime, this is one question that we got during your registration, or probably in the previous webinars, which is the major application of de-energized trip and why?
Okay, so I'm trying to go forward. Here we go. Well, I think we have covered this already, but in case it should have been missed in the webinar, the majority of the applications for de-energized trip, which was this 95 to 98% in the industry, which I already explained, is that the safety implemented functions are classically all configured in a fail to safe position. Therefore, it is that de-energized trip. And the application typically would be like an emergency shutdown system. It could be a high integrity pressure protection system or a HIP system, as you abbreviate, or it could be a BMS system. Those are all the classical systems from the process industry, which will be configured in a de-energized trip application. As I already mentioned, and I repeat it here again, just to make sure that you capture this, that is also the reason with those de-energized trip, because we actually build them. If something goes wrong, go to safe position. That means if indeed something goes wrong and I lose the power to my digital output, or I lose the power in my marshalling cabinet, or someone cut the cable to the solenoid, or someone cut maybe the instrument there to the solenoid, that is why your safety function will go to a safe position, because it was configured. If it is losing the power, go to trip. That is why when you have a spurious trip or a nuisance trip, that they are more frequent than if you would have an energized to activate, to energize the field in order to go to safe position. Is not often happening that an internal failure can still activate the outputs. That is why you need to have a little bit of an engineering skill for the energized to activate to actually achieve the safety function. Okay, Andrea, next.
Next, interested to know if the use of a SIL-rated power supply influences safety functions in fire-gas scenarios.
Thank you. Actually, this question came from the registration from the previous de-energize or energize to activate webinar from, I think from last year, if I remember well. But the reason why I kept it is I added in yellow here the bottom line. And the bottom line is because the same person, I recognize the name, was asking me again the same question. They was saying, how can I include the reliability of a power converter, power supply inside my PFD estimation for that safety loop? That's an old question. I have had this question before. It's also a very, let's say, critical question, because I do know out of experience that the majority of vendors with a reliability calculation tool today cannot take credit for the power supply reliability of that specific safety loop. So what do? They take PFDs, simply speaking, in configuration of the architecture of the loop per subsystem. In terms of the configuration, if there's a 1 out of 1 or a 1 out of 2 or a 2 out of 3 or whatever it is, they will estimate the PFD average for that loop based on your interval / coverage. But there is no package to my know-how today, and I'm limited know-how because I haven't been using them in the last couple of months. So maybe in the meantime, it is overruled what I'm trying to say, but there is no direct input in your calculation tool to enter the SIL criteria of a power supply. You can then ask the question, why do I have to buy then the power supply? Well, it's the opposite question. It's time that somehow the availability calculation of your loop that can be jeopardized because of an unreliable power supply feeder to your safety loop. It's time that those specialists who are making those equations to say how reliable your loop is start to take credit. In other words, they have to start to modify and add this additional information in that loop. How it has to be done, you have to speak to them because they are the specialist on that package. I cannot say that, but I can only wish that in the future, that question will be disappearing, that people will start to get used to use safety, reliable power supplies for their safety loops. I will not repeat all here in the middle because we have done it in the webinar, but we are saying that a normal power supply versus a SIL suitable power supply, difference lays in the middle bullet here, that the 61508 part 2 is dedicated to explain to the power supply developers of hardware and or even firmware inside such power supply that it is all about the diagnostics covering the accuracy, the under and over voltage, the latch up and high in rush current, and the overcurrent of your field devices that this power supply would be feeding. All right, Andrea, last one for today, I think.
Okay, when using a relay to interface the load of the solenoid in energized to trip function, which is the role of the DO module of safety PLC?
Well, I think I also have covered that, to be frankly, but I thought, okay, it doesn't harm to cover it twice because then it may start to filter in with the participants listening into this webinar. Digital output itself of safety PLCs is to demand the safety function to do something. And as we explained, we have two functionalities. We have the de-energized or we have the energized to activate. For an energized to activate, as we already explained, means that you have to power up the functionality enabled to execute your safety function. Now, when most DO modules are de-energized to trip functionality, but some vendors also have, of course, already pre-configured the energized to activate mixed in the same system. Such an ETA, the DO modules will have load and line monitoring inside that module itself. That is the functionality to answer the question. The role of the DO module is either to de-energize, and at that time there will be also a monitoring in a de-energize because we also want to know the loop is still there. But at least when we de-energize that module, the output is supposed to go to safe state. We are more afraid on the opposite when the digital output module in normal condition has no power to the field. If something would be wrong in the field, we would not really know unless we try to figure out that maybe the load is still there. So we're going to send like a small current in that load to make sure that we can recognize that the end of line is still there, that the impedance or the resistance is still there as a value. So we measure something like a small, call it like a small milliamp signal back to know that my loop is still impact, because we are just afraid that if we have to power it up and the load has changed or the load is no longer there, well, then clearly it will not work. So we want to be alerted from that. And that is why we have to think about it smartly. That's why I call it smartly with interface modules. So those interface modules can interface both de-energized and energized with some diagnostics. Okay, we have some more live webinars, but I think this is an old copy because it's 2020. We have 2021.
Doesn't matter. Yeah, the website is always updated, so you can check on on Gemi website or the live webinars that will be, say, organized in the next month. As Tino said, we have a lot. All of them have been recorded like this one, so you can review on our YouTube channel and also send to the people who did not attend. Thank you. We wanna launch this last poll because it's very important to know. It was very long, more than more than 1 hour, but it's impossible to reduce this time, Tino. I guess it's when there is this specific.
It's always long.
Always long.
When I start to speak, you have to try to stop. It is a challenge. I was trying an hour. It's only an hour and 10 minutes. So come on, it's only 10 minutes.
It's okay.
Extra.
It's okay.
It's okay. I have had worse. We had an hour and a half was the longest one. But anyway.
Last time mine was 1 hour 25 minutes, I guess, because there were a lot of questions and you cannot unanswer that. Thanks. Okay, thank you very much. Your answer is anonymous, of course, and thank you very much. And we don't show, but your answer is really appreciated. Thank you, Tino. Thank you very much. And maybe we wait for your participation for another webinar. Okay. Okay. Remind you just our face, our name. If you want to send, especially to Tino, some question, you have your easy mail.
Sending a question is not a problem, but getting an answer, that is a real problem.
At least we try. We try.
We do our
copy. Best. Maybe I will force Tino to answer to your question if he won't do.
All right. Well, thank you, everyone. Have a good morning,
good
night, good afternoon, whatever it is. And thank you, Andrea.
Safe. Thank you, Tino.
We'll see you soon somewhere around, okay?
Thank you. Bye. Ciao. Bye-bye.